Good evening and welcome to Digital Media E10. This is week 8 digital cameras. So today is one of the days where we're going to be able to start taking all of the information that we've learned throughout the course and start weaving it together and see how all of the concepts and all the things that we've started talking about are actually interconnected in very interesting ways. Before we do that, of course, I have the usual assignment reminders. Project 3 is due tonight. The last of the numbered projects, Project 4, is released today on the course website. So give yourselves a pat on the back for having submitted, or very soon, hopefully, submitting Project 3 and finishing strong with Project 4. Problem set 4 was released last week and is due next Thursday. We'll have one more numbered problem set, and then after that, it will be smooth sailing with only the final project to worry about. So let me talk to you a little bit about Project 4. This is an interesting project, and as you've hopefully gotten the sense, every project is very different from the others. And this one is meant to be sort of the highlight of all of the other projects. So taking everything that you've learned up until this point and producing exhibition-level quality photographs. In the past, we have had exhibitions of students' photos in various places, and it's always a lot of fun to have printouts of your photos hanging somewhere and for you to actually see them and have your fellow classmates enjoy them. And this is the project that is actually accomplished. But there's one other thing as well where you will be able to show off your photographs. For those of you that follow along from home, you may be very familiar with this. And even if you join us here locally, you've probably gone to the course website, and if you haven't yet, how? It's amazing. But anyway, you've probably gone to the course website and noticed that every time you visit, there seems to be a different photo. Right now, we have about 75, 79 something photos, each submitted by the staff members, so myself and all of the TFs, so we have a fair number of them. But one of yours will also appear here as well, and that is the first part of Project 4, is to create a photograph that can be exhibited on the course website. There's a lot of details and specifications with regard to that. Please be sure that you read the specifications very carefully. You can consider the other project technical specifications as practice for Project 4, because this one we are even more strict with the technical specifications. We give you exactly the size in pixels that we are expecting for the photo that you submit for the website. And if it deviates by even 1 pixel, it will throw off the layout, and we will have to reject it or ask you to resubmit it if you're going to actually put it on the course website. So please be sure that you look at that very carefully. Ask your TA if you have any questions, or rather just ask the staff if you have any questions about that. I'm also going to ask the TAs in sections in the upcoming weeks to talk about some of the nittier, grittier details in the project with regard to aspect ratios and pixel size specifications that we dictate there, and also some color space information, which, although is necessary to understand for this project, we're not going to be able to go in depth in lecture for a couple of weeks still. But don't worry, we will cover all of that stuff in sections. And because now we also have a section that is recorded and placed online, if you're not able to attend one in person, then do please try to take a look at that. Again, all of the links are provided here on the course website. And the exhibition is always a pretty fun way to see everybody's photographs. I realize now that I probably should have loaded the URL that contains all of last year's photos. Oh, here it is. Paste that right here. And you'll notice that a lot of these photographs are just, they're excellent. They're out of this world. And that is what we are hoping that you will also submit to us as well. We are expecting 1 photograph for the web page with pixel size dimensions specified in the project, and 4 photographs for consideration in the exhibition. And due to limited space and, frankly, limited funds, we won't be able to print out 4 times 117 students. We're not going to be able to print out 500 photographs. We will have to select a very limited number for display at the actual exhibition that we have at the end of the semester. So please be sure that your photographs are the highest possible quality. And again, I refer you specifically to the project specifications so that you can get a sense of what we're looking for there. One of the biggest gotchas about this, perhaps, is that we are expecting an aspect ratio of 5:4 for these photographs, or 4:5, depending on whether you want it to be horizontal or vertical. It can be either a horizontal or vertical picture for the exhibition photos. However, the website photo must be horizontal. We have, again, a very specific size for that. So, again, we'll talk about this a little bit more in sections, but it will be easier if you submit the correct aspect ratio and your photograph happens to be selected for that. We will be able to just print it straight away. So a lot of the techniques that you've used in your photographs will come in handy now. Any image modification that you wish is certainly allowed. You may do cropping so long as you respect the aspect ratio that we ask, and so long as you don't crop so much of that away that the quality of the image would then be hindered by the low resolution of the photograph that you submit. But we don't have quite as high of a requirement for EXIF data or anything of the like. There is one more thing that is expected in this project, and that is, along with each of the 4 exhibition photos that you submit to us, we're also asking you to submit a text file that describes that photograph. So for your first exhibition photo, you'll also have a text file for that one exhibition photograph. Again, the specific details are in the project specification, but it's basically just providing a title to that, providing some authorship information, so how you would want your name to appear if we do print that photograph, and we do print little placards for those photographs, how you would want your name to appear there. If you do not wish to use your real name, that's fine. We're still going to know that it's you based on your submission to the course website, and you can use a pseudonym, of course. But we highly encourage you to do so that if you have fans of your work, they will be able to find you and be able to request prints from you. That has actually happened in the past, so I leave that as a little tease for those of you to work really hard and achieve some excellent photographs. So as you can tell from here, some photographs may look familiar, sort of like some Project 2 photographs. We do allow at least at most one of the 4 you can reuse from a prior project or from or even just any point in time, so long as you took it. We will allow that so long as it's a photograph that you took and is representative of your highest quality work. So we don't want to make you feel as though all 4 images have to be totally new. Any questions on this before we move on? So this one is fun, I hope, and we won't get to see the results until the very end of the class. There's always a very stressful period for a couple of weeks when the staff have to vote on each of these. What we end up doing is independently voting, and then we end up doing this like massive vote where everyone has to select their favorite photographs, and then there's always arguments about which ones make the cut and which ones don't. It's very stressful for us because we love so many of the photographs, so realize that we're not going to trivialize the decision that goes into this whatsoever. This is something that we will definitely be worried and concerned about, especially since we are expecting so many fantastic photographs. But even so, we will have to not print all of the photographs that are submitted to us. If you have any questions there, then of course, please do let us know. All right, so today we're going to talk about digital cameras. So we'll get a chance to talk a bit about some of the circuitry that is inside of a digital camera, but there's some basic stuff that we actually didn't even address in this class quite yet, and I want to first talk about this by addressing this notion of dynamic range. So we talked about this common analogy that exists when we're discussing digital cameras and their dynamic range as being essentially rows or this matrix of buckets that collect rainwater that we could set outside, and we want to be able to measure how much rain we can actually collect. And more precisely, we want to know the range of rain that we can actually collect. So there is a maximum volume of this bucket, beyond which if more rain than that falls, then we're not going to know how much rain fell because we know that it reached the maximum, the bucket started spilling over, and there's nothing else really for us to be able to measure. We just know that it exceeded that amount. And there's going to be a minimum amount of rain that we can detect as well. We might have this enormous bucket and maybe just a drop or two falls. And what does that actually mean? We're not going to be able to stick a ruler in there and try to determine how much height of rain actually fell into this bucket. So there's a minimum amount that we are constrained to be able to read as well. And so this analogy, and we're really going to beat this analogy to death today, unfortunately, before we start coming back and talking about the actual mechanics of the circuitry. And again, I don't want to worry you too much. We're not going to be doing anything too heavy with regard to electrical engineering. You'll see one circuit and you'll be like, oh, look, this is the circuit, and that's about it. But it's still useful to talk about because it helps us understand what's going on behind the scenes in this digital camera. So anyway, we have a pixel in our sensor, which is represented in this analogy by the bucket, and it is collecting this rain, the photons, inside of this pixel. And really, effectively, what's happening is that this pixel is a device, is an electric device that charges, that gains voltage every time a photon hits it. So these photons that we've been talking about are these individual particles/waves that represent light, or that are light. And as they hit this specific element in this circuitry, this pixel gains a little bit of charge. And so it's this charge that we're really going to be able to measure. So there's a maximum charge that this pixel will be able to collect, and there's a minimum charge that we could read. If it's too small of a charge, we're not going to be able to read that, and it will essentially seem to be noise. And that's essentially what's happening here, is that we have a maximum volume, we have a maximum number of photons that we can actually capture, convert that into a voltage, and read off of our sensor. And there's a minimum beyond which we're just not going to be able to read at all. So let's come back to this analogy, and let's think for a minute about what if we had this huge pail system, or huge bucket system, just a whole bunch of buckets out in an open field, right next to each other. The rain starts to fall, and all of a sudden the buckets start overflowing. What happens to these buckets? What happens to this rain that are being collected in these buckets that are now over full? Not really a trick question. It just kind of spills over the side, right? But what happens if there's another bucket right next to it? It might spill over into that bucket as well. And you might have seen this in your own digital photographs. When you have regions that are so overexposed, you might get this effect called blooming, where some other areas, that overexposed region seems to sort of spill over to neighboring pixels as well. And there is actually a phenomenon that's very similar to this analogy that we're, again, beating to death, but it is this voltage that's sort of spilling over to these neighboring pixels and therefore impacting the exposure on these neighboring pixels as well. So what do you think might happen if no photons actually hit this pixel? What happens if nothing actually falls within this bucket? Well, like we alluded to earlier, we're going to have this scenario where we're not going to be able to read it. We would say perhaps, oh, this is about 0, but how many photons will it actually take for us to start to recognize that there is some amount of light, that there's actually some detail that's provided in that exposure? And again, we use this idea of the dynamic range as we modeled it like this, that there is the dynamic range is basically this ratio of the biggest signal, or the full bucket, the full quantity of photons that we can measure, divided by the smallest detectable signal. And there's a lot that we can say about this denominator here, about the smallest detectable signal. Because this doesn't necessarily mean that there's no signal. It just means that there's perhaps some number of photons that hit this before we even start to register a voltage at all. And there's actually a lot of other complications as well, in that how are we actually measuring the voltage here? What if we are measuring it using some technique that is, very imprecise? And let's say we're going to use a ruler to measure how much water we have collected in our buckets. Now imagine that we have a ruler that only measures in centimeters, or worse, even just inches. There's just a little notch every inch. We're not going to have a lot of resolution to know exactly how much rain has gone into the bucket, and we're going to be forced to round to the nearest marking. So we want to have some mechanism that is able to read this data off of a sensor in some very precise way, but also one that is able to not perhaps round to the nearest large number. These are all very important considerations when someone is designing one of these digital sensors. Of course, this is a vast oversimplification of the engineering that goes into one of these devices, but it does tell us a little bit about the dynamic range that we can get and how we can talk about the dynamic range that comes out of one of these sensors. So we saw what dynamic range actually looks like in a photograph when every time we have a scene whose dynamic range actually exceeds that of the possible dynamic range of our camera. So realize that when we say that the dynamic range of a scene, obviously a scene itself doesn't have some amount of detection signal that we're going to be dividing, but instead a scene might have some maximum number of photons coming in at the brightest areas and some minimum number in the darkest areas, and that dynamic range would be the difference between those two areas. And that dynamic range might be far greater than what our sensor is actually capable of capturing. And so we mentioned that there's a certain number of stops that some digital SLRs or some very good sensors might have. We're starting to see some in the range of, I think, 13, 14, maybe even 15 stops of dynamic range, which is really, really impressive. But the vast majority of cameras that we see these days are probably not that high, and they're probably more along the lines of 8 to 10 stops of dynamic range, depending on the camera that you're using and a lot of factors. But, I mean, obviously this isn't something that we actually think about in day-to-day life with our cameras. We are not out in a scene like this and all of a sudden trying to think in terms of the number of stops of dynamic range that our camera is able to capture. But instead what we notice is that our camera is just unable to capture the dynamic range that's contained within the scene. So it's useful to talk about now in advance of when we're actually in that scenario that we have to deal with a high dynamic range scene and a sensor that's not really capable of capturing it. But there's a lot more nuance that goes into this. So let's think about a sensor itself. And we've talked, just really alluded to the fact that that digital sensors come in a variety of sizes. And in fact, they come in, I mean, it's kind of a dizzying number of different sizes. And the relative differences between them are great. I mean, the difference between a full-size frame or rather a full frame size and the size of the sensor in your camera phone, for example, or your smartphone is huge. I mean, we are talking about very small area in the sensor in your smartphone versus that of a full frame photograph. And this actually makes an enormous difference. So for this discussion, we're going to largely ignore the differences in aspect ratio between these sizes. Sensors come in different aspect ratios. Some of them come in 4:3, where you have 4 pixels across for every 3 pixels down. A lot of digital SLRs come in 3:2, which is sort of the standard film aspect ratio. But you see a lot of things in between as well. Some that are geared for video might have something different altogether, like 16:9 or something crazy like, 2.85 to 1 or something like that. And so it really varies depending on the sensor, what the goal of that sensor was. But we're going to largely ignore that for the discussion of size. But notice here the relative difference between the square or the rectangle that's marked as the full frame, which is the largest frame inside of this light rectangle, compared to this really small one, which is called 1/2.3 inches. I mean, we're talking about a vast difference in the size between these different sensors. Now, there's a lot of reasons why we have sensors that are like this. It just so happens that larger ones are much more expensive to produce. You might recall, actually, did we show this yet? No, next week we will see a video that talks a little bit about how sensors are made. And as you'll see, they're made on silicon wafers, very much like the CPUs in your smartphone or in your computer. They're essentially just etched into these wafers. And the larger that a chip happens to be, the more likely that there is some problem in that process. And so they have to test all of these sensors, and so the larger sensors actually have a higher probability of having some sort of failure, and so it's actually harder for them to actually create this. Not even talking about the amount of material that goes into this. If you have, for a given wafer size, you have a certain number of sensors, and a bigger sensor means that you can print fewer of them on there. So these costs really compound. And this is one of the reasons why we see full-frame cameras are so much more expensive than their smaller frame cameras. But even overcoming this idea of cost, we can see that the much smaller sensors would just fit into much more compact packages. And so this is one of the things that has really enabled digital photography to take off, and why we can have devices that have such small lenses and sensors is because we do have this capability of creating sensors that are much, much smaller than full frame. Okay, so there's a lot of these different sizes. Let's point out a couple of interesting ones. There's the full frame size. Notice that there is in APS-C, there's a couple of different APS-C sizes. These are what are traditionally known as like the digital camera or digital SLR sizes. If you have a Nikon system, for example, and you have a lens that is, or rather a body that's labeled as a digital system or a digital size, then it's most likely referring to this slightly smaller size. The 4/3 system is one of the more popular or maybe more common mirrorless sizes. And the reason that it's common is that the 4/3 specification is open, and so there are a variety of manufacturers that produce 4/3 sized sensors and lenses and bodies and a variety of other things. And they get much smaller from there. So let's focus on two sizes in particular. I'm just going to arbitrarily pick two. One is going to be a small sensor, 1/2.5-inch sensor. The one on the right is going to be a more standard digital SLR-sized APS-C sensor. So I've marked here the relative sizes. So obviously these are not actually the actual sizes, but they are to scale relative to each other. We can see on the left that the height of this sensor is about 5 millimeters, the width is about 7 millimeters, and for APS-C, the height is 16 millimeters and the width is 24 millimeters. So again, let's ignore the differences in aspect ratio, but let's consider for just a second that both of these sensors have 6 megapixels. So what does that mean in terms of the size of each of these individual pixels? Well, if we have 6 megapixels, and let's just assume for a moment that we have an aspect ratio of 3:2. It's not quite right for the one on the left, but that's okay. We'll just fudge these numbers for now. If we assume that we have an aspect ratio of 3:2, that means that we have 3,000 pixels across and 2,000 pixels down. So 3,000 times 2,000 is going to be 6 million pixels for each of these cameras. Now, if you actually assume that these pixels are square, which is an okay assumption for our purposes right now, and that they fit perfectly within each of these sensors, you can imagine now that the relative size between these pixels is going to be very, very different. In fact, the relative size is going to be identical because it's the same number of pixels, same with, it all scales down, geometry and whatnot. But if we actually compute what the size of these pixels are, we have on the left 7 millimeters wide, 3,000 pixels across. This is, and I did the math beforehand, it's like 0.007 meters divided by 3,000. This ends up being 2.3 microns, which is just really, really small. That's 0.0000023 meters, which is just absolutely tiny. Now, for comparison, because people love making comparison to the width of the human hair when they talk about tiny stuff, the average width of a human hair is, guess how much in microns? Just throw out a number. Any guesses? Any hair width experts? Yes? 10, okay. 10 is a little higher. Any other guesses? How much? 30. A little higher still. Yeah. 50. Wow. No, still more. 100. Nailed it. All right. So if we have an average human hair thickness of 100 microns, of course your mileage may vary, and we have a pixel that is 2 microns, you can imagine we are fitting a lot of pixels onto this particular sensor. Now, this doesn't bode well for any of these sensors, really. I mean, we are talking about just absolutely phenomenally small sizes for these pixels. But if we compare that to the size of the pixel on the right, which after we do the math ends up being 8 microns, it's still very small, and it's still smaller than the width of a human or the thickness of a human hair. But still, we can see that 8 microns feels like quite a lot more than 2. And this is really important. Imagine if we have in some case, light that's falling onto both of these sensors. It's the same amount of light that's falling onto both of these sensors. How much less light is falling onto an individual pixel for the sensor on the left? Think about that for just a minute. We'll come back to this in a little bit. But this actually shows us something important, that if we have, there's actually many things that this shows us that are important. We have pixels that are very different in size, and that implies, as I just implied, this impacts how much light we're able to collect at each of these pixels. But even more importantly, imagine that we just have a lens, any lens set up in front of both of these sensors. It's the same lens in these cases. And I have taken a picture with this same lens in the same scene. How are these two images going to look different? We've alluded to this in the past, and the one on the left, because it's only a smaller portion of the center, will look like we have essentially cropped out all of the rest and zoomed in on that. So, do you guys remember this? We were talking about perspective changes with regard to optics and how we could perhaps crop out the center portion of an image and make it look as though we were using a higher focal length lens just by cropping out the center portion and expanding it to be the same size. Well, this is exactly the same thing, is that for the same lens and otherwise the same camera, for a sensor that is smaller, is going to crop out the center portion of that image, and once blown up to be the same size, will make it appear as though the lens on the camera on the left is more zoomed in than the lens on the camera on the right. There's an important thing here, which is that everything else was the same about these two sensors. They both have the same number of megapixels, and so when we make them the same size, they look to be, about the same relative sharpness, perhaps, unless there's any problems with our optics, but we'll ignore all of those things. But really, they look like they have different focal lengths of lenses attached to them. But that's the key word here, is that they look like they have different focal lengths. And this is the idea behind a focal length crop factor. And for those of you that have digital SLRs that are not full frame, you probably already have to contend with this, where you may purchase a lens that is intended for a full frame sensor, which means that that lens is projecting an image to fit within the full frame sensor size, which in this case is shown in red. But if you have a crop sensor, like any one of those APS-C or APS-H sensors, essentially what it's doing is taking out the center portion of that image, throwing the rest of it away, because, well, it's not actively doing that, but it's just being ignored by the sensor. There's no pixels elsewhere to be able to capture that information. And effectively, what it looks like, if I were to take the two images here that were captured by two different sensors, it looks like one is more zoomed in than the other. But it only looks like it. It only looks like it is more zoomed in. And the reason that I'm emphasizing this is that the focal length of the lens itself hasn't actually changed. It is still however many millimeters for this particular lens. But because we have this crop factor involved, we have a narrower angle of view that this lens can provide. So for a given focal length, just knowing the focal length of a lens, we don't know what the field of view of that lens will actually be unless we also happen to know the size of the sensor that's going to be capturing the image projected by that focal length. So very early on in the class, I said it would be useful to have some standard size through which we could talk about focal lengths. And this is why talking about full frame sizes is so useful, is because that is a size that many people are familiar with, and it is one that a lot of crop sensors end up multiplying or using their crop factor to determine what that equivalent focal length would actually be. So let me make this a little bit more explicit. So we have here, this is a circle because a lens is circular, and so it projects a circular image into the back of the camera. But we have sensors that are rectangular, and so it's only capturing a rectangular portion of that image. So we might have a lens that projects an image like this. It's not going to have quite as clear of an edge. Obviously, it might be a little different than this. We have a full frame sensor in red, and we have an APS-C size sensor in blue. You might also remember from the very first class when we looked at those high-speed videos of the shutter and mirror movement in digital SLRs, how some digital SLRs had much smaller sensors and mirrors. This is precisely this same thing, is that those crop sensors, those crop cameras, are so called because they essentially crop out the center portion of this image. So again, pay attention to the relative size of the red and the blue, and now assuming that these two sensors have the same number of megapixels and we zoom them to the same size, it appears as though they are different in their field of view. So this means that for digital SLRs, for digital sensors, for sensors that are not full frame, when we have to take a wide angle shot, when we want to take a wide angle shot, that we then have to have some very small focal length that may not really work in a traditional full-frame camera. So for this reason, we start to see a lot of digital-specific lenses that are designed to project their image not for a full frame, not like this big circle that fits the full-frame circle, but instead allow themselves to have limitations in their projection of that image circle. And it might not look correct on a full frame camera, but that smaller image circle would still fit very well inside of a crop sensor. So one of the reasons why manufacturers don't want you using these digital sensors, or rather these digital lenses, on full frame cameras is for this very reason, is that the image that it's projecting is smaller, and you will have this terrible vignetting on the corners. It will appear very, very dark in that image. But even worse, a lot of these are actually designed for the smaller mirrors in mind, and so they might actually protrude farther into the back of the camera, which means that a full-frame mirror, if you actually attach one of these so-called digital lenses, which are so-called because they have that smaller image size, that the protrusion into the rear of the camera might actually hit the mirror as the mirror in a full-frame camera is traveling up. All right, so we have this idea then of a crop factor. And the best way that you can sort of determine what the relative difference in size would be is just to figure out what the crop factor of your digital sensor is. And this is typically something that is provided in a lot of specifications for your digital cameras. Typically with crops, or rather with an APS-C size sensor, it's something along the lines of 1.6, which means that if you put a 50 millimeter lens on your crop sensor, it appears as though it is 50 times 1.6, or about 80 millimeters in focal length. But again, that is only in apparent field of view relative to a 35 millimeter frame. So this might explain why, for those of you that ran home after the optics lecture and looked at the information that was presented to you on the front of your cameras and the front of your lenses, this might explain why some of the focal lengths that you saw didn't match what we talked about in lecture at all. How a wide-angle lens is something along the lines of 16 millimeters to 35 millimeters, and a normal lens is perhaps 35 to 70 or so, and telephotos anything beyond 80 millimeters. But you might have a compact camera at home whose focal length range is actually much smaller than that, like 6 millimeters to 72 millimeters instead. And again, the reason for this would be because the sensor in this camera is so small that the relative or the apparent field of view of this 6 millimeter lens would be that of perhaps a 35 millimeter lens on a full frame camera. And in fact, based on this camera on the left, when we take into account its crop factor, this lens has a 35 millimeter equivalent of 36 millimeters to about 400 millimeters. So 6 to 72 is in fact 35 all the way to 432, which is actually pretty impressive for a built-in lens to have a zoom range of that size. But think about now some of the benefits of shrinking down a lot of these components. Because we have these smaller sensors and because we can then crop out the center portion of this, so on and so on and so on, that means that now we can have lenses that do have smaller focal lengths, and therefore we can then have smaller lenses that have the same field of view. So these cameras, these compact cameras, are able to achieve what they can in such a small package because it just so happens that these smaller focal lengths have the same field of view. Imagine the size of a 400 millimeter lens, which you might recall from the optics lecture was that sort of sheared in half lens that Shelley took a picture of. It looked big, and in fact it was massive. It's probably, 2 feet long or something like that, 1.5 to 2 feet long. It's heavy, it's expensive. But now we can fit all of that into a lens that can go to a maximum of 72 millimeters and have the same field of view in this smaller package. So just like all things, there's this trade-off. We have this smaller sensor. I alluded just before that maybe there's a chance that in certain cases these smaller sensors then don't get quite as much light. There's a lot of nuance there. But there is the benefit that we have all of this in a smaller, more compact, more portable package. Any questions on this? Yes?
You look at the full frame sensor and the crop sensor, and see on that mountain there was a person hiking on the mountain. If you zoomed in on both photos, it would be clearer on the full frame sensor.
So let me go back to the slide that you're referring to. So this one. So your question is regarding...
There's a person hiking on the mountains, and you zoomed in on both photos to the exact same size.
Mm-hmm.
The person be clearer on the full frame?
So if I have a person hiking on the ridge and I zoom in on both photos, which one will be clearer? So there's a lot of factors that go into this. Let's assume that these two cameras have the same number of megapixels. If they have the same number of megapixels, then arguably, because we have more megapixels in a smaller package through this crop sensor, that we then have more pixels that are able to resolve that hiker, that fictional hiker on this ridge. Which means that if you have the same number of megapixels or more in this crop sensor, that you will have a little bit more resolution out of that. But the downside is, do the optics also have the resolution to be able to support this? So poor quality optics may not actually have the resolution that's necessary for the smaller pixels in this in this crop sensor. So we end up approaching the limit of optics perhaps more quickly in these dense, small sensors than we would in larger sensors that have larger pixels. And this is one of the things that we started to see as we were transitioning, and by we I mean camera manufacturers were transitioning more and more to digital, is as they had denser and denser sensors, they started realizing that we were hitting the limits of resolution of the optics that they were providing. And this is one of the many reasons why investing in high-quality glass can help ensure that you get a very high-quality image out of that. It's very dependent on a lot of these factors. And so I would say then, ultimately to your question is that it depends, but assuming that the lens is of high enough quality, and assuming that these two sensors have the same number of megapixels, we would then be able to resolve more detail out of that crop sensor. But again, if our goal is not to zoom in as much as possible, but instead to get as much of the ridge in our photograph as possible, then our crop sensor is not going to be the best choice in that situation. Give and take, compromise, just like all of these things. But excellent question. Any others before we move on? All right, so let's come back to this, which is what we were looking at a little bit earlier. Now let's assume for just a moment that we're going to change this up a little bit. Let's imagine what would happen in the following case. Let's say that we want to now, rather than change the size of the pixels so that the sensor on the right can have the same number of pixels as the sensor on the left, imagine what happens if we keep the same size for every individual pixel. So what this effectively means is that we're going to have 6 megapixels on the right. After doing some calculations, we figure out that, okay, every pixel size is 8 microns, and how many pixels are we going to be able to fit on the left? So you do the math, and you realize that we'll be able to fit 875 pixels by about 570 pixels on the camera on the left, which isn't very great. That's not a very good resolution. But if you consider that we have this scenario, this sort of thought experiment, where we have these otherwise identical cameras except for the sensors, and we have otherwise identical lenses on these two cameras, imagine how the image would appear different in each of these cases. So in the camera on the left, we can imagine, okay, it has some particular field of view, it has some particular resolution. And if we then talk about the camera on the right, it would then appear to have more field of view. It would appear to be wider shot, and it would appear as though that picture on the left was just a subset, just the very middle portion of this image was cropped out. Now this is what's interesting, is that we now have pixels that, because of this difference, now are receiving the same amount of light at each individual pixel level. But if we go back to this idea of having a sensor with much smaller pixels that are in fact a quarter the size, then we're going to be receiving much less light. So if we have some, well, we don't even have to draw it. We can ignore all of these measurements, because the number of, if we go back to this idea of having the same number of pixels in each one, the relative size of the pixels is going to be this big for the camera on the right compared to this big on the camera on the left. Imagine how much less light every single pixel location is getting for the camera on the left. So we can actually fit, if it's a quarter of the size and width, that means that the total size is 1/16 on this side, which means that each individual pixel is getting how many stops less light? 16 to 8 to 4 to 2 to 1. How many stops? Any ideas? How many stops less light in the smaller pixel on the left? If it's 1/16 the amount of light. 3 stops? 4 stops is correct. 4 stops less light, because we go from 1 to 2 to 4 to 8 to 16. So 4 stops less light, that's pretty significant. This alludes to, but the reality is much more complicated, because the assumption that we made is actually a little flawed. I'll get into that in just a second. But this alludes to the fact that smaller sensors that have smaller pixels are maybe going to struggle, if we anthropomorphize it a little bit. They're going to struggle a little bit more to provide the same amount of clarity in terms of being able to measure the quantity of light that was there, because it's receiving so much less light. It's perhaps not going to fit into this bucket as well. Maybe that bucket is just not going to become quite as full. Now, we're using this as an example to talk about how the difference in size of sensors can actually impact the image quality that we can get. But it's really dangerous to think exclusively of the difference between these two sensors as being everything else being the same. Because as we just discussed a second ago, it's probably not going to be the same. The sensor on the left is a much smaller sensor, so to have the same field of view, we have to have a smaller focal length. But what else changes? Thinking back to our discussion about exposure and optics, if we shrink the focal length, what else changes in a lens? Let me provide another hint. Let's say I have a lens with the same f number on both of these cameras, but I've shrunk the focal length. What does that mean for the lens on the left relative to the lens on the right? Any ideas? Yeah.
You might have a smaller F number.
So so you might have a smaller f number, but what if I keep that f number the same? What is the other thing that might change? Yeah. Your ISO, but maybe, yeah. So actually, we'll come back to that in just a second. But if I have a lens that is providing a particular field of view, let's say an equivalent field of view of 35 millimeters, so I'm capturing this whole scene right here. And I have an f number of 2, just to arbitrarily pick an f number. Now I have this lens on this, or I have a sensor over here, which is much smaller. It has a very different crop factor. It has a much larger crop factor because you'd have to really change the size of the focal length. This means that I've decreased the focal length a considerable amount to obtain the same field of view in this case. To have the same wide angle, I have to change the focal length to be very small in this sensor. But remember that the f number is a ratio, so the size of the aperture itself is also changing. And this is the reality of having to think about all of the things at play when we are talking about differences in sensor size. Is that it's useful perhaps to think about at first the idea that we have these two sensors that have very different pixel sizes, and we might fall into this trap of thinking, okay, well, the pixel on the left is obviously getting 1/16 or 4 stops less the amount of light as the pixel on the right. But the reality is that we've shrunk the lens as well in order to obtain the same field of view, and therefore we've also shrunk the size of the aperture. And so the difference is not quite as bad as it actually seems, because there is this additional component of thinking about the resolution that is going into each of these sensors. So this next image that I'm about to show you is meant to solidify this idea and maybe might kind of blow your mind a little bit at first. But let's see if we can work through what exactly is happening. Now this is from a website called clarkvision.com, which is a fantastic website that goes into a lot of technical detail about the way that sensors work. And we'll post a link on Twitter so that you can actually see this, and we'll link directly to this article as well. But there's something that's very interesting when we start realizing all of this information, all this nuance that's involved with the crop factor, which is not just that we're changing the angle of view, but there's a lot of other impact that's happening on the camera as well. We have here two cameras, and this is trying to follow the same scenario that we just set up a moment ago, where we have one camera that has a large sensor, another camera that has a small sensor, and they each have different lenses in front of them. And so you might think that all other things being the same, you would have a photograph from a camera with a small sensor that appears to have, if you have experience taking a lot of photographs, you may believe this, that you have a photograph that has this really wide depth of field. This really deep depth of field if you have this small camera. And in fact, that is true. It does appear to be the case that smaller cameras, as a result of perhaps the smaller size, does in fact impact the amount of depth of field that we actually have. But as soon as you realize that what you've done by going to this smaller camera is not only changing the size of the sensor, but more importantly, changing the size of the lens, and beyond that, changing the size of the aperture itself, you get more of a clue about what's actually happening here, is that we have stopped down, or we have made the relative size of the aperture in each of these lenses very different in order to maintain the same f number between the camera on the right, which had the bigger sensor and the bigger lens, compared to the camera on the left. We also had to shrink the size of the aperture. So if you do the calculations to figure out what the actual size of the aperture for the camera on the right is, relative to the size of the aperture for the camera on the left, you can actually make them the exact same size, the same physical size, not the same f number, because it's going to be a different f number because we're talking about a different ratio here. But we actually make the ratios, or rather the actual size the same, and take care to make as many other variables the same as possible. We find out that our digital SLR is actually capable of taking a picture that also has a very wide depth of field. This is what we're looking at here. We have here a typical photograph that we would expect from a large size sensor, which is the one on the bottom, Canon 1D Mark II. This is an APS-H sensor, I think, so it's not quite full frame, but still it's close enough for our purposes. It has this field of view with a 28 millimeter lens at f3.5, 1/100th of a second, and ISO 640. But this image in the middle is a similar image that we took with a compact camera. And by we, I mean Clark Vision, the Clark Vision website. You take a compact camera, take a picture of this same scene, and it appears as though that depth of field is much larger, right? And all other things being the same, you actually find out that the size of you do the difference in the size of the pixels and do a variety of other things to make sure that the comparison is the same. We're actually able to notice that the f number of the camera in the middle is identical to the f number of the camera on the bottom. But again, this is just a ratio, and the focal length has to be much smaller on this camera in the middle in order for us to capture that same field of view. So we're talking about 8 millimeters rather than 28 millimeters, which means that f3.5 on that is going to be tiny compared to f3.5 on the 28 millimeter lens. So after we do some computation and figure out, okay, well, what f number do I actually have to set this to so that the aperture is then the same size, we change the f number to f13 on the Canon 1D, and we then have to, of course, change some of the other variables as well, because now that we've increased the f number, we're now letting in less light, so we have to take that into account by either increasing the ISO or changing the shutter speed, which is what has happened. Then we realize that we're able to take the same photograph. But it's really interesting when you realize not only that, but that the change in size of the pixels is what accounts for this difference in ISO. So for example, we have here at the bottom an image that was taken with ISO 640, whereas in the middle it was taken with ISO 50. So what this really means is that we can impact this photograph. Well, what this really means is that the camera with the larger sensor and the larger lens has a superset of the capabilities of the smaller camera. So it's not really the case that the larger sensors just cannot have the same amount of depth of field. We can account for that by changing the size of the aperture and increasing the depth of field, and we actually then are able to keep other things the same as well. So in this case, we then have pixels that are receiving less light in the larger camera because of the smaller aperture, but it just so happened to be the case that in the smaller camera, they were receiving less light anyway because of the difference in aperture. This is a little tough to wrap your head around, I think, at first. But just sort of follow these ideas logically from this first discussion of having two sensors that are otherwise the same number of megapixels, you have the same lens on each, and then, of course, one of them will then have less light. But that's not actually the reality. The reality is that they may have the same number of megapixels, but you're also shrinking the size of the lens to account for the difference in the field of view. And by doing that, really what you are essentially doing is changing the size of the physical aperture itself. And it's the size of the aperture plus some measure of resolution that defines ultimately how much of that image is going to be in focus, not so much the size of the sensor. Okay, let's stew on that for about 5 minutes, take a quick 5-minute break. When we come back, we will continue talking about the impact of pixel size on our images. Welcome back, everyone. So, I heard I was notified that I neglected to mention something really kind of important about this. I think I started talking about it and then got diverted and started talking about something else. But with regard to Project 4, not only are you submitting a photograph to be used in the course website, but also for those of you that watch at home, you may have noticed that we have like a very short intro video with a bunch of photographs that also match the ones on the website. We will start to use some of your photos in the course video as well. So you're going to get a lot of exposure, pun not intended, for your photographs through Project 4. So please be sure that you put the utmost care into the photographs for that project. All right, so before the break, we were talking about how the main idea to take away from this is that we have large sensor cameras that, through a variety of factors, are actually just supersets of the capabilities of the small camera or the small sensor cameras. Doesn't happen to be the case that we can reliably say that inherently do small cameras have a larger depth of field than larger ones, than larger cameras. It just so happens that through the difference in these physical properties, most specifically the size of the aperture, that it just so happens to be the case. I wanted to point out a couple of other things, thanks to a question that came up earlier during the break, is that the relative size between the two sensors in these photos is approximately the same as the examples that we've been talking about here. So it's been it's a difference of roughly 3.5 or so between the two. And now one of the things that will really kind of blow your mind is that we have the relative difference in pixel size between the compact camera, which is the one in the middle, and the larger camera, which is the one on the outsides, of about 3.5 or so. And that just so happens to be the multiplication factor between the F numbers. So in order to actually ensure that we're making the aperture about the same size, it's the same difference between those. And it also just so happens that because we have now made the field of view the same, because we have now made the size of the aperture the same, and because we have inherently, just by looking at these at the same size on our screen, we have the same quality and the same resolution for both of these. It just so happens that both of these cameras at every single pixel location are receiving about the same number of photons, which is kind of neat because the shutter speed is the same, 1/8 of a second. We've isolated all of these various differences. But now you might be saying, well, okay, and this is kind of interesting because one thing that appears to be different is in fact the ISO. And in fact, yes, it just so happens that now because we have this large camera that we have to stop down and keep the same shutter speed, we actually see that we have to increase the ISO to account for the reduced amount of light that we're capturing at that pixel. So the main takeaway there, what's important, is again that this larger camera is a superset of the capabilities. It is able to do this, the same thing that this smaller camera is able to do, but also you will be able to change that F number so that the aperture is then bigger, and then also change the ISO so that you can then capture more light and have higher quality image as a result. And this is an important thing, is that for all other things being the same, in particular the same generation of electronics and all of these similarities that we can make between these sensors, is that the larger sensors will generally outperform those smaller sensors. And again, lots of asterisks here because we might have some large sensors that are much higher pixel density than the low sensors, and maybe vice versa, that will go into impacting the output here. So let's then look a little bit more at the relative difference in pixel sizes. So we might have some sensors that have larger pixels, and if we're really going to beat this analogy to absolute death, you can imagine that we have wider pixels, which means we have bigger buckets. So that might mean that we would be able to capture more photons, or to capture more rain, without filling up the bucket quite as fast. So in other words, imagine that a certain amount of rain is falling, and We're trying to capture that in a bucket, and if we have this criterion of resolution, we're trying to fit as many photons in the same pixel as we are in the smaller pixel as we are in the larger one, then we're perhaps going to overflow that pixel much more quickly. Now, this is perhaps sort of the farthest away from that we will allow ourselves with this particular analogy, but it does hint at something important, which is that for a smaller pixel, we might have more difficulty in obtaining a very large dynamic range. We may fill up, quote unquote, that pixel much more quickly, and therefore have a smaller dynamic range than we would in a larger pixel. The main thing here is that we have this idea of signal that we're detecting in terms of the photons, and there's also a lot of noise that's in the system, and we are trying to measure the signal and ignore the noise. And having a high dynamic range is one way that we can have a lot of signal in that case. All right, so let me take this idea, and we've been talking about dynamic range, and hopefully you have a little bit more of an intuition for what it is. It's this idea of the largest possible signal that we can capture divided by the smallest detectable signal that we can measure on this sensor. And let me show you what happens in actuality when we actually modify the ISO on our camera. What's actually happening is that we're not actually changing the sensitivity of this, because that physical device that's contained within the sensor is only as sensitive. It's as sensitive as possible to the number of photons that it is collecting. We can't make it any more sensitive. But instead what happens is there is some circuitry that amplifies this signal. It takes this signal, whatever it is, multiplies it by some factor, and then we get out of that the value that we want to measure at that individual pixel. And so when we change the ISO on our camera, effectively what we are doing is changing that amplifier. We're multiplying it a little bit more than we were in the past. And so this alludes to this sort of huge problem. You might, as soon as you realize this, you might start to think, oh my God, I'm never going to use a high ISO ever again. But hold on, it's not quite as bad as it actually sounds. If we're taking an ISO and we're saying that our sensor is going to be, quote unquote, twice as more sensitive as ISO 100 by changing the ISO to 200, effectively what is happening is that there is this amplifier that is multiplying those same values by a factor of 2 rather than by a factor of 1. And so what this means for our dynamic range is that as we increase the ISO, we're multiplying these factors, we're multiplying these values, and eventually we hit a ceiling earlier and earlier and earlier in our buckets, in our pixels, beyond which we just cannot measure that anymore. So we have then, for a full bucket in our ISO 100, we are able to use the full dynamic range of that pixel. But for ISO 200, if we're going to make it, quote unquote, twice as sensitive, that means that we have to multiply those values of 2, which means that as soon as that pixel is half full, then we're no longer able to read anything beyond that after amplification. So this sounds really bad, because it sounds like, okay, that means I'm losing a stop of dynamic range every time I increase the ISO. And that is a little bit true. It's an oversimplification, of course, and what is actually happening is that it just so happens that as I increase the ISO, as I'm increasing this amplification, it also happens to be the case that my smallest detectable signal goes down just a little bit every time I bump the ISO. Which means that, yes, we are doing this weird multiplication thing where we're not going to be able to have the same dynamic range out of higher ISO sensors than the same sensor set to a lower ISO. But it's also not going to be quite as bad as losing one stop of dynamic range every time you increase your ISO by one stop. It's going to be a little bit less than that. But you are still losing dynamic range when you increase the ISO. And for those of you that have been using digital cameras for a long time, this was especially noticeable in old generation digital cameras, because they weren't able to optimize for the high ISO strategies as well as we are in modern sensors. And so very quickly you realized you would increase the ISO just a couple of stops and you would have basically no dynamic range. It was very easy to blow out the pixels at individual locations whenever you would have just subtle variations in the light. It was really, really frustrating. Fortunately now, as the technology improves, we are really improving both sides of this dynamic range equation, thereby making it a little bit better. This is why we're able to have improved ISO capability if we're able to have improve our smallest detectable signal at every individual pixel location and do other electronic tricks as well to try to ensure that we don't lose quite as much dynamic range at every single pixel location. So for those of you that sort of have had this maybe an intuition that when you go outside and you want to take a landscape photograph and you want it to be as clean, as noise-free, and have as much dynamic range as possible, you would try to use the lowest possible ISO. You weren't crazy. There was a reason for that. The lowest ISO that your camera can give to you is generally also has the highest dynamic range. Now there's another little asterisk here, which is that some cameras have a special low ISO setting, and that is not necessarily meaning that it is all of a sudden able to detect more signal and then divide it by 2, but it's effectively doing the division rather than a multiplication. And so be wary of high ISO or low ISO settings that extend beyond your camera's default settings, because there's additional tricks that go into those as well that might impact the quality of your image. All right. So with this in mind, I want to talk about the different types of sensors. And really, there's only a couple of things that you have to know about the different types of digital sensors that exist in cameras. Really, there's the two most prominent types are called active pixel sensors or passive pixel sensors. And you might have heard the terms CMOS or CCD. And really what this depends on is where exactly is the light amplified. CCD tends to be the most prevalent. Oops. CCD tends to be the most prevalent. CMOS just happens to be a little bit cheaper. It uses a little bit less energy, but it also is generally higher noise. But this is interesting because if you look at your digital SLR, for example, you might notice that it has a CMOS sensor, and you might say, hey, wait a minute, it seems like the opposite is actually true. But all of these properties make a lot of sense for a large digital sensor. If it's cheaper to make, then that means that it's not quite so bad to create a wafer that has a very large sensor on it. The losses will not be quite as great. Sure, it may be the case that it has a little bit higher noise, but that's perhaps offset by the fact that it is a larger sensor. It's able to capture more light. And also the fact that it uses less energy is sort of a bonus, and that's one of the reasons why we see digital SLRs in particular with CMOS sensors outperform the battery life of CCDs. But when we're talking about small sensors with really small pixels, we want to try to get as much light performance out of that as possible, so we generally will find the more expensive CCD sensors within those. But again, remember, just by the nature of them being much smaller compared to their CMOS or larger sensor brothers, means that it is not quite, it is offsetting those differences in cost. So let's just look very quickly at the circuitry of this. And don't worry about it, you don't have to know precisely what this is, but this shows a lot of very interesting things about what's happening at the pixel level on a digital camera. So this is one individual pixel, and maybe even if you know nothing about circuits, you can kind of see that this seems like a lot of stuff for one pixel. So sure, we might have a row and a column wire that allows us to read the data at an individual pixel, but you can also see that there are these transistors that exist, and there's these other wires in order to power the individual pixel, and then there's a little reset thing over in the left that actually resets the pixel, the voltage back to 0 or to whatever voltage it's reset to. But notice that among all of this stuff that we have here in the center, this little photodiode, where light, and this is the thing that actually is responsible for capturing the light in this pixel. And this alludes to yet another problem that digital camera manufacturers have had to contend with, which is the circuitry that goes into an individual pixel is kind of complicated, and it takes up space. So if I have this pixel that is maybe this size, and it can only capture light in this tiny little area, that's kind of a problem, because that means that light is falling elsewhere on this circuit, and I have to totally ignore it. I just have to not be able to capture that light. So if you were an engineer and you just had to accept the fact that the electrical engineer said that, okay, we have to have all of these transistors here in order for this CCD to actually, or this sensor to actually function. This is an active pixel sensor. How might you try to fix this problem? How might you try to shine more light onto that narrow area within a pixel? Any ideas? Yeah. What's that? Okay, so that's one idea. So we could try to build it vertically, where we have the photodiode, which is the component that accepts light, maybe at the very top, and then all of the other circuitry built behind it. That's a good idea, and that's sort of like 3D printing is an advanced technique, and that sort of idea is something that we're only just now starting to see because of the engineering that goes behind manufacturing a sensor with that particular process. But there's other ideas as well. Did I see? Yeah. Yeah, so could you redirect the light? So imagine you just have like a little magnifying glass, for example. You probably as a kid had a little magnifying glass, and you'd be amazed when you would, not fry ants by shining just that regular amount of sunlight and focusing it onto a very narrow point. And in fact, this is precisely what happens at every individual pixel. And one of the main reasons that digital camera sensors have improved so much is not just because of improvements to the circuitry, but because they have really vastly improved these so-called microlenses that rest atop every single pixel. So as part of this whole layer of circuitry and other stuff that goes on in this digital sensor, there is one of the top layers, an individual lens whose sole purpose in life is to act as this sort of magnifying lens and direct all of the light onto the photodiode, or at least as much of it as possible. And this is sort of a cross-section idea that we have to that we can consider for a sensor. We have the well right here, which is the well is the location of the pixel where the photodiode actually exists, and we want to try to focus all of the light into that well, and we want to try to focus it away from the circuitry, because shining it onto the circuitry is going to do us no good. We've lost that light. We're not going to be able to measure it. But this sort of hints to some other problem, and another reason why we have seen improvements in microlenses and improvements in the capabilities of digital cameras, which is that the light on a sensor doesn't always shine directly straight down perpendicular onto it. Imagine that we have a pixel. Imagine that we are a pixel at the far end, maybe perhaps the far corner of a digital sensor. Imagine that we have some very wide angle lens with a high aperture, for example. That light is not going to come in a perpendicular fashion, but instead it's going to come at a very harsh angle, which we can kind of see a little bit in this diagram here, where the light is in fact coming at a slight angle. And so some improvements in microlenses are not only being able to ensure that the light is then focused more precisely onto various regions of the well, but also to be able to capture light at more extreme angles as well. And we would actually see problems with this in early digital sensors, where we would have some reduction in the amount of light. Some vignetting that would happen in the corners was not just because of the lenses, but because of the angle of the light coming in at an extreme angle and not being captured as well by these extreme far outside pixels. It's kind of neat, right? It's kind of a interesting thing that some of the improvements that we've been able to make have not just been in the circuitry, but also just in this optical device that exists in a sensor. But I want to blow your mind yet again, and that is that I'm going to propose that cameras, these photodiodes, cannot actually capture light, or rather color. They can capture light. But if we were to look at a photodiode, it's not actually possible for them to know what color of light actually falls on top of them. And this is a big problem because, well, first of all, I'm making this kind of huge claim, and you're sitting there thinking, okay, well, obviously he's never looked at a digital picture before because it sure looks like it's in color to me. But we have to have some other mechanism, some other way of being able to engineer this such that we can have color at every single pixel while still having a photodiode that can only detect the intensity of light and not the frequency or the color of it. It can only detect intensity and not the frequency. This is, again, alluded to here in this one picture, in that we have this red layer which exists between the micro lens and the well, which acts as a color filter. Every pixel is designated a specific color, red perhaps, or green perhaps, or blue perhaps, and there's a filter that allows only that frequency of color to hit the photodiode, which means that if the camera knows that some photodiode has some particular voltage, and in combination with that filter, that it knows that, okay, at that pixel location, we measured so much red, or we measured so much green, or we measured so much blue. And this is exactly what we see. We have cameras with 3 filters, any one of which only exists at an individual pixel location, either a red filter, a green filter, or a blue filter, so that every pixel is then able to measure the amount of light in those frequencies at that location. So there's kind of another problem here, isn't there, which is that we have pixels, and they can detect color only by using these filters, which seems kind of like a hacky solution. Doesn't seem like a really great solution. We'll see how some engineers have come around this solution via some other mechanisms as well. But the main problem here is that we have a red filter, a green filter, and a blue filter, which are 3 filters, but pixels are square or rectangular. And so what is actually going to be the pattern that allows us to capture color and have some repeating pattern of these filters on our sensor? Something to think about. I want to show you actually a video which might give you the answer, perhaps. And this is actually a video from someone on YouTube called The Engineer Guy. And this is fantastic. I love the channel overall, but this is also a very good video because it goes into just a little bit more depth about what it actually means for CCD to function. So let's take a quick 5 minutes and watch this. And ignore the cheesy music.
Photographic technology has changed a lot in the last century. Digital photography became cheap and convenient because of the CCD, the charge-coupled device inside this camera. In the past, we'd just place a piece of film here behind the lens. But now we have a purely electronic imager to do all the work. Let me show you. Here it is, just a shiny slab, yet its details are fascinating. This CCD captures the image and then transfers it to the camera's memory system to record it as electronic data. When exposed to light, different sections of the CCD build up charge proportional to the light's intensity. We can then measure that charge and know precisely how bright that section of the image should be. If you enlarge a picture on your computer, you can easily see the tiny picture elements called pixels. Each one corresponds to a single section of the CCD. This is the essence of the digital camera. Several million of these sections of photosensitive silicon in a grid capturing an image. Now, the key to understanding how digital photography became cheap and ubiquitous lies in the ingenious way that the CCD transfers the image into the camera's memory. The easiest and most straightforward way would be to use wires to connect each pixel in an XY grid. But that presents a problem. Here's what goes wrong. After exposing the grid to light, we can use these wires to read the information pixel by pixel, measuring the charge on each section of the grid. This makes sense in principle, except all of the pixels and their electronic components leak a small bit of charge that distorts the charge coming from each pixel and leads to striations and patterns in the image. This distortion, called capacitive coupling, increases as the number of pixels increases. A CCD solves this problem in a very simple way. The pixels have no wires attached to them. A CCD is made from a slab of silicon. To make each pixel within the slab, engineers create insulating sections called channel stops. These divide the slab into rows. The surface is covered with a thin layer of insulating silicon dioxide, and then perpendicular to the channel stops, engineers deposit thin strips of metal, typically aluminum. Each pixel then is one section bounded by channel stops in aluminum. So now we have our grid of pixels. Recall that when light strikes the whole array, the silicon pixels build up charge proportional to the intensity of the light striking them. We then have a captured image stored as charge within each pixel. The great innovation of the CCD was how it moved the image from the silicon array to the camera's memory system without using external wires that would distort the image. The CCD shifts the charges from row to row without wires until they reach the bottom when a readout register transfers the charge to the camera's memory with very little distortion. The camera then counts the charges and constructs the image using that data. Now, one last important question. How do we get color? A CCD only detects total light intensity, which is useful for producing a black and white image. But for a color photograph, we need to separate the entering light into red, green, and blue. The most obvious solution is to filter the light into those three colors using three separate CCDs to capture red, blue, and green information and combine them into a full color image. However, engineers have created a cheaper solution. Instead of using three separate CCDs, they use a little math, so they only need one. In this consumer camera, they cover that single CCD with a filter with red, green, and blue pixel size sections. This creates an image coming out of the CCD that's a mosaic of these three colors. The camera applies an algorithm to estimate the correct colors for each pixel. For example, if a green filter covered a pixel, we would need to estimate the red and blue components of that pixel. To do this, they'd use the adjacent pixels and average the color intensity for the pixels in question. It works because the image's significant details are much larger than each pixel. This sounds implausible, but you've seen the results yourself. I'm Bill Hammack, the Engineer Guy. This video is based on a chapter in the book, 8 Amazing Engineering Stories.
A little bit about this. We'll talk about color filter arrays and the process that actually goes into reconstructing the image a little bit more next week. But this is actually something that does happen in each of our cameras. And in fact, for those of you that have had any interest in video, you may have seen video cameras in the past that actually advertise one of the solutions that he mentioned, which was to have three CCDs. And they actually split the image that comes in into its constituent components, red, green, and blue, split it into separate CCDs, each one of which is responsible for a red component, a green component, and a blue component, and then use those to reconstruct the original image. Obviously, that actually works out pretty well because if we have red, green, and blue channels at every single pixel, then it becomes very easy for us to be able to identify at every single pixel location what the intensity of light should be. It becomes a little bit more harrowing of a process if we actually have that pattern that exists on our sensors and have to reconstruct the color at every single pixel. We'll actually see next week that these patterns actually are different in a lot of cameras. There's a typical pattern that we see the vast majority of the time, but there's also a lot of patterns that are atypical that we will see a little bit more next week as well. But there's one other thing that he mentioned that is actually pretty interesting, especially as we get nearer to our guest lecture in a few weeks when Dan Coffey, who is producer at CS50 and does a lot of work with video, will actually give a guest lecture and show us how to move some of your skills from still photography over to using perhaps the video modes for those of you that are interested on your still cameras. But also, one of the interesting things to note there is that a lot of these cameras that we use that are still cameras that also happen to record video may have this interesting effect when there's a lot of fast horizontal movement across the sensor. You may have seen a lot of videos where everything starts to appear distorted. It kind of looks a little bit diagonal, and there's this idea of reading things off of a sensor in this line-by-line fashion is responsible for that. I'm sure we'll be able to talk a little bit more about that in the upcoming weeks. Are there any questions on any of this? Yes, we will post this the video as well. In fact, I gave it to Shelley, and it may already be on the Twitter box, whatever it's called. Tweet zone. Is that what they say? No. All right. So next week, again, we'll talk a little bit about color filter arrays and how we're actually reconstruct an image from those. Until then, I think we'll end a little bit early today. I think I gave you plenty to digest. Take a look at, in the extra time, the Clark Vision link. Try to understand that and help you get through this myth, quote unquote, of using small cameras in a large depth of field. And also do take a look at Project 4. We're very excited to see what you have to produce. And until next week, thank you all very much, and we'll see you then.